Now, if we had the central metal atom being surrounded by 6 ligands, how did we earlier visualize this? We thought of the XYZ planes, the axes, and the ligands coming along the axes to meet the metal with the coordinate covalent bonds, right? We'll tilt it a little so that you can have a good view of all of the ligands attacking the central metal atom. Now, think about a case, the general formula being within square brackets Ma6, 6 ligands of the same type surrounding the central metal. All of the bonds, any pair of bonds are adjacent to one another, are very similar. There's no concept of cis-trans geometrical isomerism in this case. What if I replace one of them and I have an Ma5B? Even in this configuration, irrespective of where B is, there is a very similar arrangement. There is no concept of geometrical isomerism. There is no concept of cis-trans isomerism for the Ma6 or the Ma5B configurations in the octahedral complex ion. Now, what if I had a case of Ma4B2? Let's explore this. Central metal atom with 4 of the A ligands on the equatorial plane and B. Now, this makes one configuration. What if I switch one of the A's and the B's? Great, so I have M, B, B, A, 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 A. Is there any difference between this structure and the previous one? Let's bring back the previous one and split this into 2. So in the first case, I have A, 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 A. The B's are opposite with respect to the equatorial plane. And in the second case, the B's are adjacent to one another. Of course, we're not considering the A's here because you see how they spread about, right? This case, where the B's are away from one another, is referred to as the trans isomer, and this case is referred to as the cis isomer. Can I have more isomers? Of course, right? Now, what if I had this B also replacing the A? I'll have 2 B's, 2 A's, A on top, A and at the bottom. Will this be a cis or a trans? You need to understand this very carefully, that this isomer is no different from what was there earlier. Because if I just rotated this while changing the XY planes and the axes, it's exactly the same as what we had earlier. Keep in mind that our depiction of the XY, YZ, ZX planes and the XYZ axis is just a model for us to be able to visualize things. Both these arrangements are cis isomers. There is no difference between the two. Likewise, I could think of trans as well in 2 different configurations here, both of which are the same. So in a nutshell, for an Ma4B2 configuration, we just have one possible trans configuration and one possible cis configuration. The very next case after Ma4B2 would be Ma3B3, of course, within the square braces and the corresponding charge. Now, how can this be represented? If I have the central metal atom, I'll have 3 ligands each of 2 different types of ligands. Now, I could arrange them in this configuration, B, 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 A, A, A. Can I switch anything here? I could also have a B, 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 A, A, A. Now, is this different from the other? Let's consider both the options, right? Now, if I were to draw or try to visualize the octahedron's faces, just like this, we'll notice that in this case, I have all 3 ligands of the same kind occupying one single face of the octahedron. And in this case, every face has 2 of one kind and 1 of the other, right? Here, where all of them are adjacent by the faces, is referred to as a FAC isomer, and these are referred to as an MER isomer. Now, face why? Because they belong to the same face, and here we say they are meridional, which is why the MER. Cis-trans isomerism as such for an Ma3B3 is understood in terms of FAC and MER isomers. Now, what about the other cases of octahedral configuration where we could have an Ma2B4? Hey, we're using general representations, right? Ma2B4 as a general type is the same as Ma4B2 as a general type. We've already covered that. But then yes, there are more possibilities, there are more configurations that we can explore. We can even have bidentate ligands. Let's explore them, take a few examples as well.